Hello, everybody. It's Mr. Covey here, and you should have watched that boring, lame limit comparison test video that Mrs. Lemke made. My apologies. Now we're going to learn the cool, fun, direct comparison test. Okay? We are having you watch both these videos because these two tests are very similar, and students always get them confused. Okay, so please pay really close attention to this, and then maybe even go back and think more about the limit comparison test, because these two tests are very similar, and we don't want you to get messed up. Okay. Before that, real quick Trivia Tuesday. I know, special video edition, right? Okay. Well, Mr. Covey's dog Penny holds the world record for the cutest dog. She does not hold the world record for the biggest dog. How much did the biggest dog ever weigh? Take a guess within 10 pounds. 343 pounds. Pretty crazy. That's a big dog. That is a large dog. All right, on to math. Okay. We just wanted to give you guys a quick reminder about P-series, or for any series in that matter. If you have a constant connected to a series, you can just take out that constant, okay? And because we're always just asking about convergence and divergence, if this series converges, then 12 times that series converges. If this series diverges, it goes to infinity, then 12 times it goes to infinity. So taking out that constant is never going to change the convergence or divergence, which is what the questions are always asking you. Okay, so that's just a general comment. Okay, this is on page 17 in your note packet. I'd like you to just take a few minutes to make sure that you can write out all the different conclusions relating to the different rules we've learned, because a lot of them are very, very similar, as we keep saying. So why don't you take a minute and see if you can fill that out, and then we'll go over. Okay, pause. This is page 17 in your giant note packet. Okay, first guy, nth term test. Remember, you take the value of the sequence, you take the limit of the sequence, and you compare it to 0. A lot of comparisons happen, so this is what I want to make sure. Take the limit, compare it to 0. If it is 0, you know nothing. The series might do anything. But if the sequence limit is not 0, then you automatically know that series diverges. Okay? For a geometric series, what is it you're comparing? Well, you're comparing r to 1. R being the common ratio of that series. If r is less than 1, convergent. R is greater than 1, divergent. Absolute value. For the integral test, okay, you are thinking about the improper integral connected with that series. And if the improper integral converges, is finite, then the series converges. And if that improper integral diverges, is infinite, then the series is divergent. For the P-series test, you're making sure that it fits that format of a P-series. 1 divided by n to some power, and you're comparing that power to 1. A bigger power means it converges. A smaller power means it diverges. Okay? Specifically, less than or equal to 1 means it diverges. Greater than 1 converges. And lastly, this is the one Lemke went over in that last video that you should have just watched. And I was just joking. It was a beautiful video. You're comparing the limit. Excuse me. You're evaluating the limit of your original sequence compared to some other sequence. And if you get a number, any positive real number, then those two series behave the same way. That's how I'd say it. They behave the same way. They either both diverge or they both converge. Okay? A lot of comparisons already. This direct comparison test is also a comparison. Okay? So we just want to make sure you're keeping everything straight. First, so another little one thing real quick. Take 30 seconds. Tell which of these is going to be bigger for positive n values. Okay. The thing we want to make sure you guys remember here is you should have gotten that this one is bigger. Why? Well, think about the denominators. Okay, so like this one's denominator is bigger, but a bigger denominator makes you smaller. Like 1/15 is smaller than 1/14 because it has a bigger denominator. So bigger denominator makes you smaller. You guys know that, but like I just want to make sure you don't get messed up with it. This one has a bigger denominator than this one, so it's the smaller one. Bigger denominator is smaller. Okay? This direct comparison test, this is going to come up, so I just don't want you guys to flip it around your head. Take 30 seconds to do this one too. N is bigger than ln of n for once you get large enough n values. Bigger denominator makes it smaller. Okay? The reason we're thinking about this is because if you're thinking about this series, and you know that this series, our harmonic series, diverges, right? We know our harmonic series diverges. And this one's bigger than it. Just stop and think for a second. Turn your brain on. This is bigger than something that diverges. Oh, wait. If something's bigger than something that diverges, then obviously this diverges. I hope that makes sense. If you're working right now, you're going to be good. We're going to formalize that idea, but that is the idea of this direct comparison test. Okay. So there is a very confusing book definition of the direct comparison test, which you are totally more than happy to read, but it makes it seem more confusing than it is. So what we're going to show you is a quick analogy that we think kind of captures it. Mrs. Lemke's analogy. Okay. So let's pretend like Mr. Covey. That does not look like Mr. Covey. Let me just toss some muscles on there. Get my cool haircut going. Okay, so let's pretend like the box is the series that you're trying to determine something about. Okay, so this is the series that you don't know whether it converges or diverges. We're going to think about it as a magic box. You with me? And I want you to think about moving that box, okay, either to the ceiling or to the floor, and think about how you do that, okay? So if you want the box to go to the floor, you need to push on top of it. You need to push your hands on top of it and push down, okay? And that would make the box go to the floor. Hands on top, pushing down. If you want the box to go to the ceiling, you need hands underneath, going up. Hands underneath, up, goes to ceiling. Hands on top, down, goes to floor. Seems simple enough. Hands on top, going up, does absolutely nothing, right? Like your hands on top can help you push something to the floor. But if you have your hands on top of the magic box and you raise them up, that doesn't do anything to the box. Okay? And similarly, if you have your hands underneath and you move them downward, that does nothing to the box. If you want the box to go to the ground, you better be on top and be pushing down. And if you want the box to go to the ceiling, you better be underneath and going up. Okay? In other words, if this is the series that you're trying to figure out something about, it's probably just easier to look here. So if you think about the magic box as the series that you're trying to figure out whether it converges or diverges, and you think about your hands as another series, okay? If your hands are pushing downwards, that's equivalent to you knowing that your hands are converge. Your hand series, that series that you came up with in your mind, converges. And your hands going upwards is equivalent to the series that you thought of in your brain diverging. Okay. If you want to push that box, that magic box, to the ground, that series that you thought of, that you came up with in your brain, your hands, has to be on top of the box. In other words, the series that you came up with, the terms in that series have to be bigger than the series that you're trying to determine whether it converges or diverges. And the second thing that has to be true, it's not enough just for your hands to be on top of the box. Your hands have to be pushing downwards. In other words, this other series that you thought of has to converge. Okay? So again, you're going to be trying to determine whether a series converges or diverges. And the way you're going to do that is by thinking of another series, a second series. The only way that second series helps you is if it's on top and it's going down. That's the only way you're going to get to the floor. The only way you're going to push that magic box, that series you're trying to figure out about, to convergent, is if you have a series that you thought of that's both on top, bigger than the series a sub n, and converges, pushes down. Or if you want to try and show that this magic box diverges, goes to the ceiling, you think it goes to the ceiling, that's what you're trying to show, then as long as you put your hands, the series that you think of is below the series you're trying to figure out, b sub n is less than a sub n, the terms are smaller, and that series that you thought of in your brain diverges, then you can show that the magic box goes to the ceiling, that it diverges. If you don't have both of the conditions, it does nothing. It's the same as putting your hands on top and going to the ceiling, or putting your hands underneath and bringing them to the ground. Okay? So you really need to check two things, that you're on the right side and that it's behaving the right way. I hope that helps you understand it. If not, you can look at the box definition, excuse me, the book definition, but I think the magic box analogy helps you. Again, if you have a series that you thought of that's bigger than the other series, the terms are bigger than the other one, and the one on top goes to the ceiling, it diverges, that doesn't tell you anything. Likewise, if you think of a series that's smaller than yours that converges, that doesn't help you. Okay? Okay. So let's actually do a problem. Check. Let's try and show that this series converges using this idea. Okay, so here's the series we're trying to determine if it converges or diverges. We think it converges. We need to think of a series that's going to be on top of it and that goes to the ground that converges. Okay? Well, something that I know converges that kind of looks like that is 1 over n squared. That's a p series. P is 2. I know that converges. So I'm confident that this converges. But just knowing that it converges doesn't help me. I need to make sure that it's on top of my box. It's on top of the series that I know. I need to directly compare it. That's why the name is called direct comparison, to the series that I know. Okay? So I need to verify that 1 over n squared is in fact bigger than 1 over n squared plus 2n. Is that true? Yeah. For positive n values, this has a bigger denominator, which means it's smaller. Okay? So because this is true and this converges, I can conclude that this converges. Because I'm on top of it and I'm pushing down. Okay? Those two conditions have to be met. Okay? Let's move forward. This is called the direct comparison test. It's really important that you make sure both of those conditions are met. I can't tell you how many times that people don't check both those conditions. That's because for the limit comparison test, there's not really like two conditions like that, and so that's what kind of makes it hard. This test is very similar to the limit comparison test. There's certain problems where you can use direct comparison or limit comparison, but there's some problems where direct comparison is the only option because you can't evaluate the limit. Okay, notice that there's no limit here. So if it's something you don't want to do a limit with, direct comparison test might be helpful. Let's do some examples together. Okay, so this is in your note packet. If you don't like the floating box thing, it's fine. The magic box, excuse me. But I do think it's helpful for understanding. Okay, so we're going to look at our series here, and we're going to try and think if we think it converges, or we're going to try and show if it converges or diverges. Okay, we're going to do it with a direct comparison. So we're going to think of something that's easy to tell how it compares to this. So it might be in a similar format. Okay, what my mind immediately goes to is, well, sine goes between -1 and 1. It's over 2 to the, I'm going to think about 1 over 2 to the n. It's a similar series. Okay, I know that 1 over 2 to the n converges. It's a geometric series with r equal to 1/2. That totally converges. Now, the only way this series is going to be helpful, since it's pushing downwards, it converges, is if it's on top of this function. So the next thing the next thing I need to do is think about the terms, and I need to make sure that this is in fact pushing downward, is above this series. It is allowed to be equal to for certain values, but in general, This is true. Check. Sine goes between -1 and 1, so sine squared is between -1 and 1, or sine squared is between 0 and 1. So this is true. Check. Okay, so this totally works. Now let's work on writing out a nice justification for this. So, like with limit comparison test, this relies on you clearly stating that you know that the one that you're comparing it to, you know whether it converges or diverges. You should start with that. So I'd start with the fact that 1/2 to the n converges. So start by saying that. How do I know that? Well, I need to explain why. It's a geometric series with r equals 1/2. So the absolute value of r is less than 1. I need to say that. And not only does it converge, but it's pushing downwards on the magic box. It's pushing downwards on this guy. It's above this guy. 1/2 to the n is greater than or equal to sine squared of n over 2 to the n. So since it pushes downwards and it's on top, I'm allowed to use this direct comparison test. Okay? So then I can conclude, therefore, my original series converges, and I should name drop direct comparison test. Oops. Converges by direct comparison test. Again, you'll see people write like DCT. Just write out direct comparison test. That's the way you should do it on the AP test. Just write it out. It's not that much short. Okay. If you're thinking that this just seems more complicated and harder than limit comparison test, there are some times when it is, and that's why Mrs. Limke said she likes the limit comparison test, because it is a little more straightforward. But this is a good example where if you tried to do limit comparison test with 1/2 to the n, you'd get a limit that you can't evaluate. Okay, so limit comparison test doesn't work for this, but direct comparison test does. Cool. Also, I hope you recognize that this is very messy. So like something like integral test, no. Too messy. Okay, again, we're kind of getting far in our giant flowchart of our different techniques. So this is an example of a series you'd come up to and like you'd try some stuff, but this is messy. So a lot of the strategies that you might try don't work. Okay. So you kind of would filter down to direct comparison tests. Okay. What could you compare this to? You got to think about something similar. Whenever you're doing direct comparison tests, you think of a series that's similar. Well, this inside part, n over 3 to the n plus 1, it kind of behaves like, goes to 1/3 basically for big N values. So this whole thing kind of behaves like 1/3 to the n. That's what I'm thinking. Okay, I'm thinking about it's somewhat similar to this series. Okay. Now remember, in order for this to work, I need to make sure that I know what this does and that it's pushing the right way. Okay, like I need to make sure that I'm on the top pushing down or on the bottom pushing up. So what does this do? Well, this is just a geometric series with r equal 1/3, so this converges. Now I need to make sure that it is pushing, or excuse me, that it is on top. I know it pushes down, I need to make sure it's on top. In other words, I need to make sure that this is true. And you better think hard about this, because this is where kids mess this up, because they kind of just say like, yep, that's true, and they move on. And a lot of times it's not. It's the hands on top going to the ceiling, hands underneath going to the floor situation. What's a good way to think about this? Well, they're both to the n power. So I can really just think about what's bigger, n divided by 3n plus 1 or 1/3. Well, is that true? This is going to have a denominator that's a little bit bigger than this one's denominator. A little bit bigger because that plus 1. A little bigger denominator makes it smaller. Okay, so this is true. Bigger denominator makes it smaller, this works. Please go through that process, making sure that it's pushing down and on top or pushing up and underneath. Okay? All right, so I'm all ready to roll. Let's write out a nice justification here. Why don't you pause, try it, and then I'll show you. Okay, so since This series converges because it's a geometric series with r equals a third and the absolute value of r is less than 1. And it's greater than, the terms are greater than the terms in the series I'm looking at. Hence it shall be known, thought that sounded kind of fancy, that this series converges by direct comparison test. Okay, so your justification needs to be like a full sentence looking something like that. Cool. Again, I can't emphasize enough, this is just another option. Maybe other tests work and we're going to get to the point where we'll look at a series and we'll have like 2 or 3 different ways to do it easily. But this is just another tool in your toolkit. Again, trying to do limit comparison tests with this would be kind of messy because this is a complicated function trying to do a limit of. Yeah, at least it looks messy to me. Okay. When you're thinking about what to compare series to for direct comparison tests, there's really 2 good options. I mean, there's lots of options, but the 2 good options are the 2 easiest types of series to tell whether they converge or diverge, and those are geometric series, like we've done for the previous 2 problems, or p-series, because those are very easy to tell whether they converge or diverge. For this problem, I'm going to go the p-series route. I'm going to compare it to 1 over n. Okay, I know it looks a little different, so it kind of takes a little bit of a get a feel for it type of situation. Okay, but I'm going to compare it to this and watch what happens here. First, I know this diverges. Harmonic series, it's a p-series of p equals 1, it diverges. Since it diverges, it goes to the ceiling. I need to make sure that it's underneath this guy. Okay. In other words, I need to make sure it's underneath this. Again, I can't emphasize enough, this is tough to tell. I can't glance at this and see whether this is true. I need to make sure this is true, otherwise I cannot use this direct comparison test. Okay? How do you figure out if this is true? Well, let's think about it. If this is smaller, then its denominator should be bigger. I will say that again. If something is smaller with the same numerator, the denominator is bigger. So I want to see if this is true. How am I going to tell if that's true? Well, I can rewrite it. The ln of the ln of n, is that smaller than n? Well, that would be equivalent to deciding whether e to the n was greater than the ln of n. Right, I'm just going to use my exponent, flip it around from logarithm to an exponential. And I can do that again, and so that would be equivalent to trying to determine if this is true. Is e to the n bigger than n? Yeah, totally true, right? Like 2.7 to the 2.7 to the third is bigger than 3. Okay, so this totally works. Okay, again, there's not really a check that you have to show aside from stating it. Beyond that, the checking that you're doing is to justify for yourself that it works. Okay. All right, so I'm good. Write out a justification, and we'll compare. Okay. So I said since 1 over n diverges, it's a p-series of p equals 1. So it goes to the ceiling, and since it's underneath the series I'm trying to figure out, the terms are smaller than those. I know that this one diverges by direct comparison. Okay, make sure your justification looks something like that. Again, this is a messy series. So what this direct comparison test really helps you with is series that you really don't want to mess with otherwise. Okay, I don't want to do a limit with an ln of n. I don't want to integrate ln of n. Okay, so this direct comparison is a nice way to deal with it. Why don't you pause and give number 4 a try. Okay. Structure looks a little different. I'll give you a little hint. Monadnom. Okay, so why don't you pause, give that a little try, come back and we'll chat about it. Okay, so here are my kind of like initial thoughts. Before I'm writing down my justification, we're just going to kind of think about it. I'm in non-denominate, I got addition in the numerator, and I know I can do that. And the other thing that happens is like I get some canceling. So when I do my non-denom, the right fraction is just becomes a series that's n over 2, or n over n times 2 to the n, which is 1 over, it's just a geometric series. Cool. So one of the 2 series is super easy to deal with. The other one, 1 over n times 2 to the n, it's a little trickier. But when I'm looking at that, I'm like, wait, that has a bigger denominator than 1 over 2 to the n. In other words, it's smaller than 1 over 2 to the n. And I know that 1 over 2 to the n pushes down. It converges. So since it's on top and it pushes down, it's going to push this to the ground. So this is also going to converge by direct comparison test. Okay? I'm going to write out a nice justification. Here's a concise version. Or I could say overall that this series converges because it's the sum of these two series. And both these series converge. It's the sum of two convergent series. I know this one converges. I did direct comparison test with 1 over 2 to the n. I know 1 over 2 to the n is convergent because it's a geometric series. Oh, by the way, that other one converges because it's the same series instead. Okay. We will do a lot of practice with this direct comparison test as well as the limit comparison test and making sure to tell them apart. But it's definitely going to be a tricky one. Okay. Don't worry, we'll do practice with it. Thanks for watching, guys.